Welcome to qnawire.
A 350 kilogram roller coaster starts from rest at point A and slides down a frictionless loop-to-loop. The car's wheels are designed to stay on the track. In question A, we want to know how fast is the roller coaster moving at point B. And in question B, we want to know how hard does it press against the track at the same point. So we're going to solve question A using energy conservation. So the energy at point A will solely be equal to potential energy because there is no kinetic energy. And the potential energy at point A will be equal to the mass of the cart times g, the gravitational acceleration, times the height at this point, where HA here is equal to 25 meters. At point B, right here, the cart will have a reduced potential energy, but will have gained some kinetic energy, such that the sum of these two energies will still be equal to the energy at point A. So the potential energy at point B will be equal to the mass times g times the height at point B. We're at point B, we're at height of 12 meters. And the kinetic energy at this point will be equal to 1/2 times the mass of the cart times the velocity squared, where the velocity is precisely the quantity we want to determine, the velocity at point B. So due to energy conservation, we have that energy A is equal to energy B, which means that mg times HA will be equal to mb times hb plus 1/2 m times the velocity at point B squared. So now let's solve for the velocity at point B. We'll find that the velocity at point B will be equal to the square root of 2 times g times HA minus HB. So with HA equal to 25 meters and HB equal to 12 meters, we'll find that the velocity at point B is equal to roughly 16 meters per second. Now in question B, we want to know how hard is the cart pressing against the track at point B. So what's happening at point B is that there is a centrifugal acceleration, or centripetal acceleration that is pushing the cart towards the track. And this acceleration will be significantly stronger than the gravitational acceleration so that the cart doesn't fall off the track. And so the balance of these two forces will be equal to how hard the cart is pressing against the track. So at point B, we have a gravitational force equal to mg downwards. We also have a centripetal force equal to the mass times the velocity at point B squared divided by the radius, where the radius here is going to be equal to 12. Because the diameter of the loop is equal to 12. Excuse me, the radius will be equal to 6 meters. Because the diameter is 12 meters. So the net force will be equal to the difference between the centripetal force and the gravitational force. Which will be equal to the mass times the velocity at point B squared divided by the radius minus g. You're using the velocity we've just determined. In point A, a radius of 6, and the mass of 350 kilograms, we obtain a net force that is equal to 1.14 times 10 to the power of 4 newtons. So this is how hard the cart will be pressing against the track.